Welcome to qnawire.
Okay, so this problem we're given a position vector as a function of time for its x and y components, and we're being asked at what value of t does the velocity vector of the dragonfly make an angle of 30 degrees clockwise from the x-axis. Okay, so we want to find the time for the velocity vector when theta is 30 degrees. Okay, so that's for part A. And then for part B, it's asking at what time calculated in part A, for the time calculated in part A, what's the magnitude and direction of the dragonfly's acceleration vector? Okay, so once we have velocity, we can get acceleration then. Okay, so the first thing we want to do for part A is to find the velocity vector. So if we have the position vector, to find the velocity vector, we just take the position vector's derivative. So take the derivative of each component of the position vector. Okay. Okay. So take the derivative of the I hat part first. So if we do that, the first term is a constant here, so the derivative of that is 0. And then for the second term here, we have a coefficient out in front, and we can look at the derivative of t squared. Well, the derivative of t squared is just going to be 2t. So we have 2t times the 0.0900 meters per second squared. So that's going to give us 0.1800 meters per second squared. And then times t. Okay, so all I'm doing is just take the derivative of the I hat part here. Okay, this is the x direction. Now do the same thing for the j hat part. So we have negative 0.0150 meters per second squared times t to the third power. Well, derivative of t to the third power is just going to be 3 t squared. So we have 3t squared minus the coefficient out in front here. So if we compute that derivative, we're going to have a negative 0.0450 meters per second third. And then we're going to have a t squared then. Okay, so that's the j hat component. Okay, so now we have the derivative. So now we have the x and y components of the velocity vector. So now we know that the relationship between the angle, which is the direction, and the x and y components is going to be tan theta is equal to Vy over Vx. Okay. So now what I can do is I can plug in the values. Okay. So here we know the angle is going to be 30 degrees. So we have to keep in mind though, so in the problem it says it's clockwise from the positive x-axis. So if it's clockwise here, you can just draw a little diagram here. So if it's clockwise, that means the angle is here in the fourth quadrant. Okay, so that means we have to have a negative tan of 30 here. Okay, because it's in the negative y quadrant here. So if we went counterclockwise up here, then we'd have a positive tan theta because we're in the first quadrant. But since we're in the fourth quadrant down here, we have to have a negative. Okay, so we have negative tan of theta. Okay, so this is the velocity vector here. Okay. So now we already know Vy. So Vy is the y component of the velocity. So we can just plug that in. And I'm just going to get rid of the units now, just to make it simpler. And then we have Vx, which is the x component of the velocity vector. So this is going to be 0.1800 times t. Okay. And this theta here I could plug in as 30 degrees here. So let's plug that in. Okay. All right, so now we can compute these values. So if I compute negative tan of 30 degrees, well, actually the negatives cancel out here, so don't worry about them. So cancel out that negative and this negative. So I have tan of 30 degrees, which is going to be 0.577. And the t squared and the t here I have. So the t cancels out, and the t squared just becomes a t. So then I divide these two numbers here. I'm going to have 0.25 times t. Okay, so this time t ends up being 2.31 seconds. Okay. So it gives me the time for the velocity vector so that it makes an angle 30 degrees clockwise from the x-axis. Okay, so that's part A. So now for part B, it's asking what's the magnitude direction of the acceleration vector. So we get the acceleration vector from the velocity vector then by taking its derivative. Okay, so we'll take the derivative of the x component. So derivative of 0.1800 times t is just going to be 0.1800. Okay, now let's look at the y component. So for the y component, I have a t squared here. So take the derivative, that becomes 2t, and then it's multiplied by the coefficient out in front here. So if I do that, I'm going to have a negative 0.0900. That's going to be meters per second to the third. Times t. Okay, so that's going to be the j hat direction. Okay, so now I have the acceleration. So now I know the time from part A, so I can plug in t is equal to 2.31 seconds. So I plug in t, I'm going to get 0.18 meters per second squared. So it's the same for the I hat direction. And then if I plug in 2.31 seconds for the j hat part, I'm going to have a negative 0.21 meters per second squared. That's in the j hat direction. Okay. So now I have acceleration vector in terms of x and y components. So now I want the magnitude and direction of that. So I'll start a page now. So the magnitude of acceleration, take the square root of the x component squared plus the y component squared. Okay, so I already know the x and y component from the previous part here. So I plug in those values for I and j, and we get the magnitude of acceleration. So I plug them in, I get magnitude of 0.28 meters per second squared. Okay, and now for the direction. I'm going to do arctan of the y component of A divided by the x component of A. Okay, so the angle theta gives me the direction. So again, I know AY and AX from this page here. So I can put in those numbers. I'm going to take arctan, and I'm going to get an angle of negative 49.1 degrees. Okay, and the angle is negative, which means that it is clockwise from the positive x-axis here. So this is positive x. So since it's negative, it's going clockwise. So we could say this angle is 49.1 degrees. clockwise from the x-axis, from the positive x-axis.